Hello everyone, I am Vishnu Sharma and today I am going to present our work on using graph neural networks to learn decentralized planning for multiple robots. This is a joint work with Lifeng Zhu, Professor Ribeiro and Professor Kumar at University of Pennsylvania, Shinbiaoli and Professor Prorok at University of Cambridge and my advisor Professor Tokekar at University of Maryland. This work is motivated by a multi-robot target coverage problem where each robot has a tracking sensor, for example a downward facing camera. The camera can identify the number of targets on the ground. Here we use the colorful dot to show the targets. Each robot has a set of candidate actions from which it can choose one action to follow to cover the targets on the ground. As you can see from the figure on the right, robot 1 has 3 actions, robot 2 has 2 actions. If the robot 1 goes on right, it covers 2 targets, and if robot 2 goes on the left, it covers 3 targets. But jointly they cover 4 targets and they have a coverage overlap, which is because of the target T3. And in an ideal scenario, they should account for the overlap and take some different actions so that the overlap is minimized and they can maximize the number of targets covered in a joint fashion. However, the centralized greedy algorithm cannot be directly applied into the constrained communication scenarios. For example, robots have a limited communication range, so that they can only communicate locally. Here, the dashed lines represent communication links among robots. The centralized greedy algorithm requires that the robots share information such as targets covered with each other or with a central server. So it does not work in this setting with local communications, since the robots can only share information with the neighbors. To address this issue, some researchers have designed the distributed versions of greedy algorithm. For example, with this sequential greedy algorithm, robots can make decisions sequentially and each robot selects an action based on the action of its previous neighbors. Another branch is the consensus-based algorithm where robots share information and action selected with the neighbors over multiple rounds until they reach the convergence or common knowledge. But to maintain the half suboptimality bound of the centralized algorithm, these distributed greedy algorithms typically require communication graph to be connected. In other words, if the graph is not connected, the performance can be arbitrarily bad in some cases. So instead of designing other distributed greedy algorithm, we seek learning-based methods to tackle this problem. The method should consider the local communication, and it doesn't require the community constraint among robots. We found graph neural networks can be a great fit for this problem because of its decentralized communication architecture, and it does not require the communication graph to be connected since it learns from the centralized expert, and the learned policies can be applied into the graphs that may not be connected. Many earlier works have used graph neural networks successfully for similar problems on flocking control, path planning, and task assignment. Decentralized coverage with these networks have not been explored as well in comparison, which also motivates our work. The goal of this work is to design a graph neural network based learning framework that learns the mappings from robots' observations and the communication graph to predict the robot's actions. We want the learned actions to be as close as possible to the action selected by the expert algorithm, for example, the centralized greedy algorithm. Here we did not use the optimal algorithm as the expert algorithm. Because the submodular optimization is a combinatorial optimization problem, one way to find the optimal solution is to enumerate all possible combination of the robot actions, which is very computationally intensive when the number of robots increases. Also, the centralized greedy performs very close to the expert algorithm. We will show that later in the evaluation section, and therefore we use centralized greedy as our expert algorithm. We also show that our framework is both scalable and generalizable, and therefore is a good alternative to the centralized algorithm while being decentralized in nature. Generally speaking, graph neural networks are an extension of convolutional neural networks for graph data. For example, an image can be considered as a special case of graphs where pixels are connected to adjacent pixels. For each pixel, the 2D convolution takes the weighted average of the pixel values of itself and the adjacent pixels. These adjacent pixels are ordered and have fixed size. Graph convolution, on the other hand, aggregates the value of the node features of itself along with its neighbor. Different from image data, the neighbors of the nodes are unordered and the neighborhood size can be varying. And this property is very important. It first shows that GNN has a decentralized architecture, and second, it enables the learned policies to be generalized to previously unseen scenarios as long as we have similarities or the symmetries in the graph. Here is an overview of our graph neural network based learning framework. It has three main modules. The first module is to process the local observations and generate a feature vector for each robot. Then the second module uses a GNN to aggregate and fuse features from k-hop neighbors for each robot. The aggregated information is passed to the third module to select an action for each robot by imitating an expert algorithm. The first module is used to process the local observations of the robots. Each robot has two types of observations. The first one is to measure the relative positions to the nearby robots using a LiDAR sensor. And the second one is from the camera. As mentioned earlier, once a robot selects an action, it can cover a subset of the targets. So this camera's observation is the set of targets covered by all the actions of the robot. Then we transform these raw observations to two handcrafted vectors and then concatenate these two vectors as the input tensor. Finally, the input tensor is fed to MLP to generate a feature vector for this robot. This MLP has trainable parameters. Once we get the feature vectors, we use the graph neural networks as the second module to aggregate features from k-hop neighbors for each robot. For example, when k is equal to 1, robot I communicates and collects features from its one-hop neighbors, robot 1 and robot 2. Again, you can see GNN has decentralized communication architecture. And this module GNN has trainable parameters. Here, L is for the L layer and K is for the k-hop communications. This fuse information is passed into the action selection module, another MLP. This module is used to predict the probability distribution over the candidate action for each robot. The action with the maximum probability is selected. This MLP also has trainable parameters. Here the action selection is paired with the ground truth selection from an expert algorithm, and it is trained by minimizing the cross entropy loss between the predicted action and the expert action. Here we summarize the objective of the algorithm. We would like to learn the mapping from individual observation and the communication graph to the predicted actions, such that the cross entropy loss between the predicted actions and the expert actions is minimized. As said before, we have the trainable parameters in the processing module, GNN, and the action selection module. As you can see, this is a GNN-based supervised learning approach. To validate this framework, we did some simulations in this multi-robot target coverage scenario. Here, each robot has 5 candidate actions: move forward, backward, left or right, or stay idle. Each robot has a square field of view. Once the robot selects an action, it sweeps and covers some targets on the ground. As you can see from the video, each action corresponds to a rectangular target region. Each robot also measures the relative position to those robots that are within its sensing range. We compare our GNN-based learning approach with 4 other algorithms. The first one is the expert algorithm, Decentralized greedy. The second one is the optimal algorithm, which uses the brute force search to enumerate all possible cases to find the best solution. The third is a decentralized version of the greedy algorithm, and the last is a simple random algorithm that selects action randomly for the robots. Here for GNN, we set the communication hop to 1, which means each robot communicates with its one-hop neighbors only. Since the optimal algorithm was only feasible in small-scale cases, we compare the performance of this algorithm in small-scale settings only. Here we show a qualitative example of the expert algorithm and the GNN trained using it. The key difference here is that the expert algorithm is able to minimize the overlap in covering targets because of its centralized nature. This means it can identify and coordinate among all the robots, including the ones that are not within each other's communication range. Here the robots have a tracking region larger than the communication range, which increases the chance of overlap in the coverage. GNN is still able to do a good job at reducing the overlap by learning from the expert algorithm. It attains a good performance despite not having the global information like the expert, making it a good decentralized substitute for coverage planning. Next, we will look at a detailed analysis to see if GNN truly learns the patterns and doesn't just prescribe random actions. whether it makes what makes it a preferable algorithm over the expert algorithm despite the differences in performance, and if it fares well against a decentralized counterpart. Here is our small scale comparison where the number of robots is small, such as 4, 6, 8 and 10. The GNN was trained for 20 robots only and tested on these scenarios. We compare both the running time and the coverage performance of the optimal algorithm, centralized greedy, decentralized greedy, GNN, and the random algorithm. From the plot of running time, we can see that GNN runs much faster than both the optimal and centralized greedy. Here the running time is plotted on log scale. You can see when the number of robots is 8, GNN runs 1 order faster than centralized greedy and several order faster than the optimal. Also, its running time is always around 1 millisecond regardless of the number of the robots. This is because GNN has the decentralized communication architecture and the robots only share information with neighbors, so it scales well. Even though GNN runs much faster, it achieves a coverage performance that is close to optimal and centralized greedy and better than the random algorithm. Another interesting observation is that centralized greedy performs very close to optimal but runs several orders faster. And this is why we choose centralized greedy as our expert algorithm. It is cheap, but it can generate comparatively good training data. We also evaluated our algorithm in large scale setting. Here we removed the optimal algorithm since it runs very slow when the number of robots is large. Here we see similar results. GNN runs much faster than centralized greedy. Its running time is still around 1 millisecond even though the number of robots is increased to 50. It covers a similar number of targets as the centralized greedy algorithm and covers more targets than the random algorithm. We trained the GNN with 20 robots and tested it on the same and larger number of robots. We can see that GNN maintains its fast running time and near expert coverage performance. This shows that GNN can be well generalized to large scale settings. In comparison to decentralized greedy, GNN has a slight advantage in coverage, and as the number of robots increases, GNN scales better than decentralized greedy, making it a better decentralized alternative than the classical algorithm. Since it's a learning-based solution, we further evaluate the generalization capability of GNN. We train and test GNN with varying number of robots and record its coverage ratio. Here, the coverage ratio is computed as the ratio of the number of targets covered by GNN to the number of targets covered by centralized greedy. Here, the environment size is scaled proportionally to the number of robots, but the density of the targets in the environment is fixed. We can see that in all scenarios, GNN maintains a similar coverage performance around 88-89%. This again demonstrates GNN's generalization capability even in previously unseen scenarios. To summarize, in this work, we formulated the problem of using GNN for submodular maximization for target coverage. We designed a GNN-based learning framework that processes the robot's individual observations and aggregates neighboring information to select the actions for the robots. We demonstrated that the performance of our GNN-based learning approach is close to the expert. It has faster running time, and it is scalable for both smaller number of robots and the larger number of robots, and it also generalizes very well. Looking ahead, We want to use our framework in a more sophisticated simulation environment and also test in a real environment. The current design uses handcrafted features, and therefore this work highlights how GNN can improve the communication among robots. We can further benefit by using the neural networks for processing richer information representation like image occupancy map, which will make it a more powerful alternative to classical algorithms. We believe we could get more benefit in problems which have more constraint, like maintaining connectivity or resilient coordination against adversarial attacks, where classical algorithms have a hard time in finding solutions. Therefore, we could use this network to act as a good initializer and learn to solve tasks in more complex paradigms like RL. Lastly, we wish to prove that GNN can preserve submodularity, since we want to use GNN to represent submodularity of the team performance. We think this is doable since the aggregation step is a linear combination of neighbors feature. So as long as the activation function is concave, the mapping function should be submodular. Thank you all for attending this presentation. We will be happy to answer any questions at the end of the session. Also feel free to reach out to us with email. We'll be glad to discuss this work in detail. Thank you.